Forward, back. Okay. Good afternoon, everyone. Happy to be here. Thank you very much for inviting me to give me the opportunity to talk about hadron polarization. I changed the title slightly from hadron polarization to hadron polarization. So all the nice experiments that we are anticipating for the EIC require tools. And I wanted to bring to your attention the development of some of these tools and maybe also some of the problems that we will be facing in the future regarding the development and further development of these instruments. I moved to BNL August last year. I've been working at the German Research Institute for 25 years. I could retire end of this year regularly in the German system, but my desire to continue physics was like stronger than that. So, I mean, as you are young in the field, I mean, it's really a good choice. Physics is a good choice because it opens opportunities really down the line. Even like at my age, you can still go for the challenge. You can still identify the issues, work on stuff. So I'm really happy to be here to talk about stuff that I partially worked on. Okay, so this is supposed to change. Another idea. Not working. Oh, no. This way. Fine. Very good. Okay, so brief introduction to the electron-ion collider. Not too much because most of the motivation has been presented. I focus on polarized particle beams, actually going back to the very beginnings, talk a bit about hadron polarimetry and have an outlook for you. So the dominant physics questions have been elaborated during the workshop. This is like emerging nucleons, intrinsic spin distributed in space inside the nucleon. Like what role does the nuclear medium play? And how does it affect the gluon and the quark distribution? And this question that came up this morning also about gluon saturation. So there's lots of material available. You worked on that during the workshop. So this will be the machine. So it's going to be a collider colliding like ion beams, protons, helium-3, gold, lead, uranium with electrons. I would actually add here already deuterons because we can also make them. Deuteron is a spin 1 particle, so it will add information about the spin structure. The luminosity is there, 10 to 34, and we want beams with high polarization. Both beams should have in excess of 70% polarization. So the way you do this, basically, you want photons polarized longitudinally or transversely with about 50 to 275 GeV. That's 50 GeV is like close to injection. Electrons preferentially longitudinally and bring them to collision in first one detector, which will be down here in IP6. Now, okay, you want 275 GeV protons, but at the polarized source, the energy of the protons is just 10 GeV, 10 eV. And how do you make them in the first place, and how do you get them up to flat top so that you can actually use them for your experiment? Okay, so this brings me to that part here, polarized high energy particles. And I want to start with a short historical excursion on how we know about polarization. So this is the 1922 setup of the Stern-Gerlach experiment, which was carried out by these two guys, Stern and Gerlach. Basically has an inhomogeneous magnetic field. They send a silver beam from an open through slit system along the knife edge, and they, without magnetic field, they saw just a single dot, and with magnetic field, they saw two discrete up and down like orientations. And this experiment showed for the first time that you actually have space quantization of angular momentum. So that's a new that led then in the following to understanding that as a new degree of freedom, later called electron spin. Actually, the idea of the electron spin was only put forward way after the experiment, after Goldsmith and Uhlenbeck had found evidence for half-valued spin. And the delay was mainly due to the fact that they measured the magnetic moment of the silver atom to be about one mu b, one Bohr magneton, appropriate for the angular momentum of 1 h bar, and this factor 2 compensate this Thomas factor wasn't known at that time. So they didn't really have full understanding and didn't want to publish it at that time. So this is actually pictures from Frankfurt. There's a new building and they received the Nobel Prize for that in 1943. And it's kind of funny to see how lab work was taking place at that time with a cigar in the lab. There's actually a nice book put together by Horst Schmidt-Böcking, who is a professor at Frankfurt University, about Otto Stern. It's unfortunately in German. The translation is like physicist, lateral thinker, and Nobel Prize winner. So it's a nice reading. Okay, so the classical experiment basically, you see that there is a spatial splitting of the silver beam in inhomogeneous magnetic fields. Classically, you would expect that that full little ellipse is completely filled because of a continuous energy distribution, but apparently this is not continuous. So these surprising two discrete energy levels appeared, and this means that the quantum mechanical dipole clearly behaves completely different from the classical. Okay, so let's talk about magnetic moment and mu b and mu n. In a magnetic field, actually, the energy of the system is proportional to the flux density. The proportionality constant is the coefficient of the magnetic quantum number in the direction of the field. So that's the direction of the quantization. And this can either be measured in units of the Bohr magneton or the nuclear magneton. So that means you have either a mu j or a mu I. That is a typo here. There. So the experimental, this is this dying, could this be?
Yes, but we have a backup.
Okay, no, I think it's if I don't press too long. So these are the numerical values. And the convention is that for positively charged particles with a positive G factor, spin and magnetic moment are parallel, and for negatively charged particles, they are. Okay, one can now write down, say, the classical and the quantum mechanical expressions. And generally, the magnetic field splits into 2s plus 1 components with the magnetic quantum numbers going from ms going from minus s to plus s. So in the case of hydrogen atoms, this is called Zeeman effect, as observed in the Stern-Gerlach experiment. And the forces acting on the spin components on an inhomogeneous field are different, and they, of course, depend on the sign of this ms. So therefore, this idea of spatial separation of spin states is actually an ideal spin filter for particles. So you can actually use this principle to polarize a beam, nuclear polarize a beam of atoms. And in the following, I'm basically going through here. So for practical applications, actually, you wouldn't want a Stern-Gerlach arrangement, say, only in one dimension. You would want something that is radially symmetric so that you can exploit basically your rotational symmetry of the system and use appropriate multipole fields so that you don't get more intensity out with diaphragms that kind of eliminate the wrong components and only transmit the wanted states. So a Stern-Gerlach filter acts as a nearly perfect polarizer. So that means if you after a Stern-Gerlach polarizer, you basically have in a strong magnetic field close to 100% electron spin. And of course, this has limits as long as the particle velocities are low. So thermal, you need to have a magnet system that does that efficiently. And the width of the beams have to be small enough to be separable. So there are technical issues. I go through some of this in the following. So the width actually is a consequence of the velocity distribution behind the oven usually. Okay, so this is the full picture of the energy levels of the hydrogen atom. So let's go through here from the left side. So this is the Bohr picture, Rydberg formula. Then if you go one step further, you kind of have the fine structure, splitting of spectral lines due to relativistic corrections to the Schrödinger equation. Then as a next shift comes the so-called Lamb shift, which comes about from interactions between virtual photons and the electron moving around in the nucleus. Then as next thing, you have the hyperfine structure, which arises from the energy of the magnetic dipole moment from the interacting dipole with the magnetic field generated by the electron. And when you then apply in addition a static field, you get the so-called Zeeman effect. So these ground state splittings then split up further depending on the spins. Now, the hyperfines, that I'd like to now discuss a bit, the hyperfine structure of hydrogen and deuterium. So what I do in the following basically applies to an electron spin of 1/2 with a nuclear spin 1 or 1/2 for hydrogen and deuterium. You can write down the angular momentum state vectors like F and MF. This is total angular momentum. You can write down the eigenvalue equation. And if you do all that, you see at the end that the hyperfine splitting kind of can be expressed as this quantity. And there's this interval factor, which is 3 for deuterium and 1 for hydrogen. And usually you would be interested in nuclear polarization. So that means you would prefer to expand everything in MJ and MI, so the electron spin and the nuclear spin. And if you do that properly, you basically get this MJ, MI expressed like that. And then you can write down the complete Hamiltonian, like components of hadronic nuclear and some other factors, ignoring the quadrupole moment interaction. And when you do that and solve it, you get out what's called the Breit-Rabi formula. So this is a simple expression for the energy of a system depending on the nuclear spin for J equal 1/2. You can kind of, this parameter X here is basically a dimensionless quantity. For practical purposes, you can ignore the GI and the gamma I, they are really small. So effectively, this X is just the B over a critical field. I explain in a moment what this is. And so basically, you can measure then the magnetic field in units of this. And this formula allows you to have a universal representation of the Zeeman effect of hyperfine splitting, which does depend only on the spin structure. So it doesn't involve anything else. Now, if we look at this, what we get are the hyperfine splitting on the left side here for hydrogen and the hyperfine splitting on the right side for deuterium. You see here on the left side, basically for X equals 0, no magnetic field. This is kind of ground state splitting. And then you see that the state with F equal 1 splits up into 3 states. F0 stays 1 state, and with deuterium, which has like F equals 3/2, the upper branch splits into 4, and the F equal 1/2 splits into 2. And now you can see here these different quantum numbers. So this is F and MF near in the weak field region. And in the strong field region, you would expand into MI, MJ, and you see that this upper state here is all for positive electron spin, nuclear spin up, nuclear spin down. So this is spin up, proton, spin down, proton, spin down proton, spin up proton, and similarly over that on that side. Okay. So the relevant fields that I would just want to show are basically for the ground state is basically this splitting here. And for hydrogen and deuterium, this basically corresponds to a say to the critical field. And this is for hydrogen, it's about 50 millitesla. And for deuterium, it's about 11 or 12 millitesla. And the 1400, this is this famous 1420 megahertz line, which does a F equal 0 to F equal 1 transition. And for deuterium, this correspondingly is 327 megahertz. Okay, so now we have a way to calculate the polarization. So you basically can calculate the combination of each of these hyperfine states, basically using the Breit-Rabi formula, take the weighted average of the occupied particle states in the beam, and then just compute that. So for the conventional definition of the height of the vector polarization, you basically have the number of particles in state up minus down over the sum. And for deuterium, you need, as deuterium is a spin 1 particle, so it has kind of 3 orientations in a magnetic field. You need one more quantity, so you have, besides the intensity, so you have like the vector polarization, and conventionally this is the so-called tensor polarization. The star here denotes that this is the polarization with respect to the quantization axis. That can be the field in an ionizer. So if you send this atomic beam into an ionizer and you ionize it, there's a certain magnetic field orientation in that ionizer, and that defines basically your quantization axis. It's a quantity that is independent of magnetic field. And of course, the PZ, the P star and the P star ZZ both enter the figure of merit in an experiment. So while the counting statistics usually goes with square root n, it is linear in these quantities. So you have like, it's compared to the square root n, it enters with a quadratic weight. So it's important to consider that these quantities should be large in your experiment. Okay, so now if you have hydrogen deuterium in weak and strong fields, you can just look at the BMT, at this equation from Breit-Rabi, basically compute the polarization, and you see you get to this table. I don't really want to dwell on that much. So this is now as function of x, the vector polarization of the different states for hydrogen, and on the right side for the deuterium and tensor polarization of deuterium. And what you see is that there are two field-independent states. These are the so-called pure states, where you basically have a constant slope in the Breit-Rabi diagram. Yeah, if you come out of the Breit-Rabi diagram on the left side, let me just go back. If you come out on the Breit-Rabi diagram here with the horizontal slope, of course, the polarization there is small because you have a different effective magnetic moment, and therefore these states start on the low field side with 0. If you go to a strong field, all of these states are fully nuclear polarized. So one way to also express this is that you can talk about the effective magnetic moment. So that is what I plot here now. The effective magnetic moment is essentially the slope of the Breit-Rabi graph. So this delta over dB of the energy of the hyperfine state is called the effective magnetic moment. And of course, as I just explained, you don't see that on these pure states, while in the mixed state system you have a strong dependence of the polarization on the field. Now let's talk a little bit about multipole magnets. So I already mentioned that usually you would like to do that in a two-dimensional system with a cylindrical symmetry. So conventionally one would use quadrupole magnets or sextupole magnets for that. And yeah, well, I should say here that the principle for a polarized ion source for use in accelerator was kind of first formulated by Clausnitzer. I think it was in the 60s. He was a professor at University of Gießen in Germany. And now in these 6-pole magnets, you have a lens-like focusing action, and you can actually really do an atomic tracking kind of tracing in the magnetic field to optimize these systems. So you have beam transport, phase-space emittance, like you have it in charged particle optics. The same you do with atoms in to make a source. Okay, so basically what you start out with usually is you make hydrogen and deuterium in a ground state. You take a dissociator tube, apply some RF, put in hydrogen molecules, and out come, with a high degree of dissociation, hydrogen atoms. You pass these hydrogen atoms through a 6-pole system and get your desired spin separation. And then if you don't like what you get, you can still apply so-called RF transitions in the beam to make the polarization, to maximize the polarization. So I'm going to discuss the first aspects here. I will not talk about ionizers and also not about targets in detail. Okay, so historically, as I mentioned, these spin state separations were one-dimensional. Of course, you can do this much better with the rotational symmetry. Actually, modern sources not only use permanent magnets, but they also use electromagnets or superconducting magnets. And today, most of all these modern permanent magnets are so-called Halbach magnets, Halbach magnet arrays. So I'll show in a moment what this is. Let's talk a bit about quadrupole magnets and 6-pole magnets. So basically, quadrupole magnet, 6-pole magnet is self-explanatory. This describes the magnetic potential. It has this R to the M power times cosine phi term. Multipole order is M equal 2, M equal 3. The main difference I'd like to emphasize here is that for the quadrupole, the field gradient, which is the force, is actually independent of radius. Why? If you do that in a 6-pole, you gain because your gradient is proportional to R, which basically means you have here a constant deflection force, and here you can actually have harmonic or hyperbolic trajectory along the beam like you do in other charged particle optics. So a little bit about the multipole magnets. Before 1980, mainly multipole magnets consisted of separate pole pieces, like they were formed by one permanent material, like with high remanence, alnico or permandur, vanadium permandur. And typically they look like this here. So this is a view in the direction of the magnet. It's about 25 centimeters long. You see it's quite an open structure. But the fields that could be reached with these types of pole tip fields, which means really the field at the very tip of the magnet they were only about Tesla. One could not overcome that at that time. Since then, there have been developments, basically rare earth material, so-called neodymium iron boron magnets. They were developed by Sumitomo, and I think all the current magnet manufacturers that make them basically have the rights to do so from Sumitomo. And so these magnets allowed a new type of design because you can magnetize them in arbitrary direction, and you can cut them without losing anything on the surface, somehow on the magnetization. So that means you can now do magnets with smaller surface area and less outgassing. You can do so-called Halbach magnets with M segments of changing magnetization. So this is from the magnets we built for the source that is one source that is used in Jülich, and the similar magnets are used at RIG in the H-jet. And so what you do here basically is you advance your polarization segment-wise from one segment to the other. to still form a perfect 6-2 pole. And the reason that we did this was that you would really want to get the most field on the pole tip here out. You see this nice radially symmetric 6-pole structure on the center. And therefore, we were using 3 different magnetized materials to make sure that they don't demagnetize in the presence of their own field. So these 1, 2, 3 are different magnet materials which either have a higher coercive force or a higher remanence, depending on how the field calculation showed us the internal field inside this element would be. So this is the design, which is still, I think, probably the best 6-2 pole magnet design that is currently available. So, and that's just a table of the dimensions. So we have like really small inner diameters down to 10 millimeters, and the fields we can reach currently with these magnets is about close to 1.7 Tesla. So the progress in this field is measured really in small units. But if somebody comes up with a way how to make much stronger magnets, we can build much better sources. It's limited by the magnetic field that you can use to separate the spin states. So currently, really, these permanent magnets are the best way to produce a large field gradient on a small diameter. You cannot do better with even with superconducting magnets, because they usually require windings and coils, and you can get that close. There's a colleague of us in Novosibirsk who's running a polarized source which uses superconducting magnets, and it's actually inferior on the level of technology compared to modern 6-2 pole magnets. Okay, so this shows the design of a magnet system. Like these are the individual magnets. So you see conically shaped at the beginning. Here's the nozzle where the beam comes out. Down here is the target. The whole thing at that point was about like 2 meter long, 1.5 meter long. And you can see that one can do optimization calculations really to perfect the transmission of the system. And here we had like, you of course must make assumption about the beam temperature. So typically the nozzle temperature for such sources is on the order of 60 to 80 Kelvin. And this calculation was done here with 6 6-2 pole magnets, 1.5 Tesla pole tip field. And actually we built the source, and does what it should. Let me talk a little bit about RF transitions. So when you come out of, when you come at this point here out of the magnet, or when you're roughly still in here in one of these magnets, the polarization in the beam is actually 0. Every individual atom is highly polarized, but because of the magnetic field actually pointing in all kinds of different directions, you have 0 polarization. So what you have to do is actually you have to guide this atomic beam adiabatically into a region of uniform magnetic field, and then all these individual magnets will nicely line up and produce a high polarization. Yeah, like the values that I showed on this earlier slide 23, this is they're quite close. Okay, so then if you want to change the polarization or change, that basically means you have to change the hyperfine state population. And there's this method of Abraham and Winter. I think this is probably also from the 60s, so-called adiabatic fast passage. And this technique is actually employed in all sources to make a high polarization. And these transitions are, because they use all a magnetic field gradient, they are kind of independent of the particle velocity. So the way this is done is that basically you have a pole piece which is opening, so you have a field gradient along the beam. You apply an RF field. If that RF field hits the proper frequency, the atoms recess torque-wise from up to down. So this way you can make a transition between 2 hyperfine states. And then of course that is basically an exchange of the hyperfine state population. But if you do this behind the 6-pole system, yeah, you only have states populated with a positive MJ. So only the upper part of the hyperfine diagram is populated. And now if you reverse once in an adiabatic passage kind of transition, you can basically invert the nuclear polarization of the beam. Okay, so you can either apply to one state or to the other state. In this way, you can make a fully polarized, close to fully polarized, nuclear polarized atomic beam. So let me see, I think, yeah, okay, there's a little bit on classification. So usually these transition types are classified depending on whether it's in the weak field, medium field, or strong field compared to the critical field. So these transitions are typically 5 to 15 megahertz or up to gigahertz in frequency. There's a different classification scheme, which is basically refers to the quantum numbers in the transitions, whether you have the B field, the rotating B field perpendicular or parallel to the static field. I don't need to look into this in detail. So this is how it actually looks like. So you have a region here where you can do weak field transitions, medium field or strong field transitions. And so that basically means when you come out of the magnet system with these two states populated, like Mi equal plus half and Mi equal minus 1/2, yeah, and you make a transition from, for instance, state 1 to state 4, or state 1 to state 3, one could do. State 1, yeah, state 1 to state 3, then you would end up with two MIs that are both either negative or positive. So this is a nice way to actually produce high polarization in the beam behind the magnet system. And once you have that, you need to ionize that beam, and that's it. You just inject it into an accelerator. So this is the way all the sources that are used work in principle anywhere. So this is the source that is available at BNL, an advanced polarized proton source. Uses similar principle, so it produces a high beam polarization of 80% with like close to a milliamp of current in one bunch to feed one of the bunches in the machine. Okay, now I wanted to talk now in sequence a little bit about the particle optics in rings. I think there was a lecture by Christoph. Somehow he probably covered some of that. I'll look at this maybe with a little bit different, from a different point of view. How much time? How am I doing with the time? Any idea? It's 2:48. What does this mean? How much time? Half hour?
About a half hour.
Okay, very good. Okay, so you have the Lorentz force, which in a magnetic ring is responsible for your orbit. So you need to keep the particles on a circle or on the closed orbit. There is a closed orbit. Beam has a certain size and momentum spread. Particles oscillate in the lattice, and the phase ellipse and the emittance in the beam are invariants of the motion. So you can actually, that's due to Liouville theorem. So wherever in the ring you measure the phase space ellipse, say, or the emittance, you measure the same quantity. You can actually you must make sure that there are no beam instabilities. So beam instabilities basically come about when your horizontal or vertical working point hits one of these resonance lines. It basically means that if you go around the ring in one turn, you have a small magnet perturbation, that this causes kind of a resonance catastrophe. It kind of amplifies in the next turn, Therefore, there are these exclusion regions where you would like to not operate, which is basically on these lines, and somewhere in between you actually do well. Now, regarding the spin, the particles precess in the spin. There is a so-called Thomas BMT equation that basically describes the spin motion in the ring. It basically goes with G gamma. So in the transverse field, the spin precession is proportional to G gamma. So the proton has a G of about 1.7928, and the gamma, yeah, is E/m. So the particles will precess around the spin. So, and this can also cause difficulties. I come to that in a moment. So there are similar to the orbit resonances, there are depolarizing resonances for the spin in the ring, and therefore you have to make sure that you basically avoid certain conditions. So there are so-called imperfection resonances. Simply when gamma G is unity, which means you go around the ring once and you end up with your spin vector pointing exactly in the same direction as before. And if that happens, then a tiny perturbation somewhere on the orbit would cause you to actually have a similar problem than you had with the orbit. It would depolarize. So you try to avoid the so-called imperfection resonances. And there are intrinsic resonances which have to do with the periodicity of the machine, where this gamma G should not be, say, an integer times the periodicity. Periodicity means it's how many symmetric pieces you have in the ring. So if the ring is composed like of 10 sections that look identical, your periodicity is like 10, so you would enter 10 here. And the new Y is the vertical tune in this case. So I'd like to avoid those to be sure that your beam is polarized. This is an example from COSI actually, where this is just the 3.3 GeV machine. Still, you want to accelerate up. This is like the momentum on the way up, and you see here gamma G equal 1, 2, 3, 4, 5. This is where the depolarization would take place if you're not careful. And so the imperfection resonances are these fixed energy resonances here shown in red, and in green are these intrinsic resonances. And now this shows the polarization as function of momentum. So you need to really work to get these out of the way of these intrinsic resonances. You can actually make one of these resonances strong, one of these intrinsic resonances so strong that you can actually make a reversal of the polarization, which is not a problem for the experiment as long as the efficiency is high. So this is how this looks like in a low energy machine with relatively moderate number of depolarizing resonances. So now let's move to the relativistic heavy ion collider, where the G gamma is like 270 or something. So that is the maximum G gamma. So that means you have to overcome a whole gigantic grass region of where depolarizing resonances can occur to get the beam actually up to the 250 GeV. And so let's go through here. So you have the polarized source. Okay, going to a 200 MeV Linac. Here's the first time you measure polarization. You go into a booster, go through the AGS, which existed before RIG, which was the machine at BNL, which did spin physics and other stuff before like 2000 or 1998, I think. And now you have these P collisions here, one beam clockwise, one beam counterclockwise, with all these experiments in there. And you have, I explain this in a second, you have certain tools like absolute polarimetry measurement, peak carbon polarimetry, I'll come to that. And you have certain tools to make sure that you can really bring the beam highly polarized to final energy. The way this is done is you use so-called Siberian stakes to do that. And what this is about comes in a second. So this is the top lattice of the machine. Kind of, you see the clockwise and the counterclockwise beams, they are kind of meandering around. And the green ones here are all imperfection resonances up to the maximum energy. And the blue ones down here are all intrinsic resonances up to the final energy. So there's a whole multitude of resonances which one has to overcome. And the way to do that is, I mean, you can call this resonance mitigation. It goes back to an idea from Derbenev and Konratenko. I think, I'm not sure, Derbenev is still at JLab. One of you is from JLab, he's still at JLab. I met him last year. I don't know whether Konratenko is still around. You may know, I don't know. But anyways, the idea is the following, that you actually can make the spins flip particles coming in with a spin up, and then they make a funny orbit excursion plus spin rotation, and they end up as spin down. So if you do this properly, you basically have you can arrange in the machine to have half integer spin tune, which means all these depolarizing resonances, which usually come as an integer, whatever number, are avoided if you run this properly. And this is what makes RIG unique on a worldwide scale. It's the only machine worldwide where you can have a 250 GeV beam highly polarized. No other machine is able to do that. So I go in. So this shows the windings of an AGS snake. The AGS for polarization retention also has a partial snake. It's not a partial snake, means the spin is not rotating by 180 degrees, but by some smaller angle. It still helps because it moves the spin tune away from unity. So this is at AGS. So this picture here is a snake that was built for AGS. Okay, now let's look through here. There is spin motion, which is the top one is the B field here. The down one is the position along the snake. And this shows the spin component. So as I said, you come in with SY, SX, and SC are 0. And you go through with this funny Siberian snake excursion, and you come out with the minus SY, and SX and SC is still 0. And if you run this properly, you basically, you need to operate these snakes. It's more than one in the ring, of course. If you do that properly, you can really overcome the resonances. So this shows a picture. I have one with higher polarization. This was the first 250 GeV beam operation in 2009. You see all these resonance locations here, and here you see the p-carbon polarimetry, chrononuclear interference polarimetry as function of energy. And it's kind of okayish already, but it's like maybe it's just 0.5 or 0.4 or something like that. The goal for EIC is 70%. Okay, so you get your work cut out, part of you at least, to get up there all the way. This is what EIC promises to the community for both beams, electrons and hadrons. Okay, so in addition, the experiments may not necessarily want transverse spin. Yeah, the experiments usually want longitudinal spin or transverse spin, so they want the full flexibility. So the stable spin direction in a typical circular accelerator, as the bending fields in the dipoles are vertical, spin says about the vertical bending fields, and so the natural spin orientation is longitudinal. The natural spin orientation is transverse. Okay. And so if you want longitudinal polarization, you need to use the same device, powered a little differently, that are described as a snake. You have the same device that basically acts as a spin rotator. So for instance, at the Phoenix and at the STAR experiment, there are these spin rotators in place, and they convert a vertical polarization into a longitudinal one. So you see the similar orbit excursion powered differently, but you can make out of an SY and an SXC equals 0, essentially an SC. This is what the experiments want, to collide head-on at the collision point, longitudinally polarized electrons, for instance, and longitudinally polarized protons. Now, once you have done that, you can actually inject another spin state from the source, like the down spin state, and it will automatically make antiparallel. So you don't have to do anything. You just have to sit at the source and flip the polarization from up and down. And what the experimenters get is longitudinal forward and backward automatically. You don't have to. Once it's set up, it works like that. Okay. So this is polarized beams at EIC. Okay, this is what's planned. Stores typically take 8 hours in there, and beams, of course, are bunched. At the moment, RIG runs with about 110 or 120 bunches of this of this in this region. And for the EIC, this will be increased to about 1,300 bunches. And so the bunch separation will be 10 nanoseconds, which also means that we will reduce the beam current in each bunch, but the number of bunches will be enhanced by roughly a factor 10, and in total, there will be about a factor 3 or 4 more beam current in the machine compared to what is now done. Okay, so the requirements regarding polarimetry, as I said in the beginning, we need polarization, absolute polarization determination, delta P over P with a 1% accuracy, which is challenging because at the moment, RIG isn't really doing that. We have maybe 2% or something. We are not there yet. So that really has to improve. We have to work on that. There's other things to consider, like you have a polarization decay, which means you have a finite polarization lifetime over the 8-hour store. So polarization slowly disappears on some time scale. The experimenters want bunch by bunch polarization. So essentially you want the polarization for every bunch. It is known that the polarization, or that the bunches have a polarization profile, both longitudinally and transverse. One needs to know this, in particular when you collide the beam with electrons, because the electron beam is tiny, and depending on where you hit the proton beam, you really need to know what is the polarization at that location. That's why you need the profile. Of course, polarization during ramp, I measured that polarization vector at the experiment. Yeah, this is another issue. At present, RIG provides only the vertical component of the beam polarization. I mean, I did an experiment like 30 years ago to measure the complete spin vector of the experiment, all the components. In PP scattering, that's doable because without violating parity, because the PP spin dependence actually allows for that. So if you open the space to align the target polarization along each direction in space, you can completely get out the full spin vector. This is currently not done, but it should be done because it will provide a tool to be able to study the spin evolution in the machine. Like you can then actually change something in the ring, and at the measurement point, well, it tells you, okay, now the spin points this direction. If I do this and that, points this direction. It's another level of optimization. To get to 70% routinely, you have to do that. At least that's what I'm saying. So, and then there's more to come. I mean, this is a gigantic field. It's a real big field. So the physics program actually includes options beyond protons. So the experimenters would want a spin 1 particle at some point. I mean, that's already clear. That there are certain observables, spin observables, like was discussed maybe during your workshop, where you would benefit from having a spin 1 particle to collide with, like deuterons. And then also the idea to have spin half particles, but in a different nuclear environment, like in a helium-3 nucleus, which you would also want, which is the helium-3 has a similar magnetic moment than protons. So I think if the ring works for protons, it will also work for helium-3. That's not a problem. But the deuteron has a G factor, which is 0.16, which is so tiny that the snakes wouldn't work. So that means you cannot even build snakes with the field strong enough to make it work for deuterons. So therefore, with deuterons, there is really a technological issue that has to be solved, how to get this up to 250 GeV without polarization and still without polarization loss and still have everything under control. So there's a lot of work that needs to be done, and the clock is ticking. I mean, if this should be there, like by 2032, at least the ideas. If we don't start soon on these questions, it will not even be an option because the timescales are long. It might take 10 years to develop a device like that. I mean, I've been following on the helium-3 beam development. So there is a group from MIT who built a helium-3 atomic beam for a different experiment, which has meanwhile disappeared, so we can have the source. And This development actually took close to 10 years. So the timescales are long. We need to really get moving. And all the young people that I see here, if any of you has an interest in experimental physics to work on some of these issues, it's really absolutely needed. Otherwise, the physics that you've been discussing during the last 2 weeks, well, it just won't happen. It's really important. Okay, let me talk a little bit at the end about hadron polarimetry. So, okay, yeah, you have a bunch of particles traveling in the ring close to speed of light. And every bunch comes around after 78 kilohertz or 13 microseconds. And you then basically measure the number of spins up and down. And up minus down over the sum, in this case, 12 minus 4 over 12 plus 4, whatever, is 50%. So you want something that is higher, of course. But essentially, you would want to do, you really need to do a separate experiment in the machine to determine the polarization. You need a sample of scattered particles large enough to have a conclusive statement about the polarization. And of course, only a fraction of the scattering probability depends on the spin. So the spin-dependent cross-section usually is written as a spin-independent part plus a spin-dependent part. And this parameter is maybe only 3, 4, 5%. So it's not a too efficient effect. So usually what you measure in the end is like an asymmetry in the detectors, which is like expressed in terms of these sigmas here, but in practice, these sigmas mean rate. So it has a certain number of counts in each of these up, down, or states. Now, the correct frame to describe that is usually a right-handed coordinate system. So you have longitudinal n, normal n, and sideways s, and this plane is in the scattering plane. So it's like left-right detector. So you have a certain polarization in the beam. You have a God-given parameter that tells you, okay, this is the so-called analyzing power, and then you measure an asymmetry in your detector system. Yeah, and this asymmetry is like left minus the right over the sum. Fine. Of course, in full glory, this is more complicated. But the important thing is that for elastic scattering, time reversal applies. So it's known that in elastic scattering, T violation is suppressed. There is some T violation, which is on the order of 10 to minus 7 or so. But for the practical purposes, T violation is conserved here. That means whether you have a reaction with a polarized beam on an unpolarized target or unpolarized beam on a polarized target, the parameters are exactly the same. Scattering parameters are exactly the same. Analyzing power is exactly the same. You just have to make sure that you measure the same elastic scattering. So this basically means that if you measure an asymmetry in your detector system here with the polarized beam, yeah, you get a certain epsilon beam, left minus right over left plus right. And now you do the same, measure it with an unpolarized beam and a polarized target. Get the same asymmetry or get a different asymmetry, the polarization will be different. And now the way we do this is we have a way to determine the polarization of the atomic beam, like I described before, that passes through the hadron, through the proton beam, and the polarization of the atomic beam is known to probably better than 1%. So we can basically convert the polarization of the target with the measured asymmetries to the beam polarization. I mean, if you don't take anything away from this, this is what you should take away. It's a beautiful idea that you can use identical particles to get the polarization out. And the same has to happen for deuterons. So when we do this with deuteron beam, we just need to do DD scattering. And we have to identify DD scattering, measure the deuteron polarization in the target, measure these two asymmetries, if we can, and get the beam polarization out. And helium-3 is the same. So helium-3 would be helium-3 elastic scattering. Okay, this shows, so this shows what we are presently using. There is some analyzing power in the region of 100 to 250 GeV, which appears in the so-called Coulomb nuclear interference region. It's where the amplitudes of the electromagnetic and the hadronic interaction kind of interfere constructively. And this makes, for my test, still small asymmetry or small analyzing power. It makes about 4. This is momentum transfer T. So it's all this is close to 90-degree scattering angle. So it just makes 4%. I mean, the advantage here is really that you have a calculable way to determine this this quantity. I'm not sure that its quantity is calculable as well for DD scattering and for helium-3 scattering. But this needs to be done also. This, I think, the first thing probably find someone who can help us at least determine the quantities so that we can make progress. Okay, I think that's that's what I just said. So the recoil comes essentially out at perpendicular to the beam direction. And so this is the system, how it looks like. This is the atomic beam source I was talking about for the first part of the talk. So this is essentially the top half here. 6 dipole magnets, spin state separation. This green thing here are 2 transition units, a strong field and a weak field transition unit, which allows us to either make spin up or spin down at the interaction point here in the middle. We have about 120 millitesla holding field, into which the atomic beam adiabatically moves so that all the particles coming out of the source really are nicely aligned. And this says here holding field. And so there's a detector system left, right. And down here, there's a Breit-Rabi polarimeter, which is used to determine the polarization of the atomic beam. Okay, so this shows the detector system left, right of the atomic jet. This is the atomic jet. So you have a left and right set of detectors with about 12 vertical strips, pitch and thickness. One of these elements looks like that. And now this is the same idea here that I explained already earlier. You basically measure this quantity or this quantity here, or say the asymmetry once with the polarized beam and with the polarized target, and that basically gives you the polarization. Then you can also form asymmetries when the beam is not passing through, or say when the bunch is not passing through, and then you can also get coincidence or rates in to determine the background, and this is how it's done. So this shows measured polarizations. I think this was done much later than 2009. So you see here, fill by fill, the polarization as function of fill for the yellow beam. This is one of the beams in the ring, and for the blue beam, and the polarizations here kind of are of the order of 0.6. So still some way to go to 0.7, but this is typically what we would see right now. I think in the current run it's not 0.6, it's like another 0.5. Fine. So the difficulty is that the hydrogen jet polarimeter produces 5 to 6% error in 8 hours. So you need a full fill to get the polarization to 5%. And this is really bad, because you would like to have something that's fast, maybe not calibrated, but fast. So the way to do that is to have so-called carbon polarimeters. They allow really a fast measurement, like you drive through maybe in 20 seconds, something that I show you in a second, and then you get like a quick polarization measurement of that out. So this is how it is done. You have thin ribbon targets, carbon targets, typically 100 nanometer thick and maybe 10 micrometer long. You have the target holders like shown down here, and you move them horizontally through the beam or vertically through the beam. There's a set of 2 target stations for each of these beams. So for the yellow, you have a horizontal and a vertical, and for the blue, you have horizontal, vertical, and you can measure the polarization, basically moving these targets through the beam and have a similar detector system, left, right, up, down, to get the polarization out. And this is needed, will also be needed for the EIC, because you still need the fast tool to determine the beam polarization. You don't want to wait a full store to get something accurate, but not knowing what's going on in between. Okay. I think this is a bit about background. I don't want to. Okay, so there is an issue that the increased beam current, which we are going to apply, so as I said, about 3 times more total beam current in the beam, which means these carbon targets will see a much higher current. And it is at the moment not clear whether these little fiber targets actually survive. So they have been used for 20 years, but under different conditions. So we currently are setting up a little experiment to determine really the temperature of the targets, to be able to properly extrapolate this to conditions that we will have at EIC. The sublimation temperature for carbon is of the order of 2,200 seconds. So for RIG, this kind of works. But to me, it looks like for EIC, it might not work. If this doesn't work, then we really have to think deeply about an alternative. Because if these carbon targets don't work, then we wouldn't have a fast tool. And you cannot do really the development of the machinery without such a fast tool. So we need an alternative. If it turns out by the end of the current run that carbon targets likely are not an option for EIC, we really have a problem. So another one. Okay, so I'm at the end, a couple more slides. So the requirements for EIC, kind of absolute beam polarization, polarization decay, transverse profile, longitudinal polarization, polarization vector, bunch polarization. So you see that with the jet and the carbon, we can essentially cover most of it. There's an additional idea to detect forward neutrons, as there were large asymmetries measured in proton-gold collisions in the forward direction. So we try to have a test sometime during the current run to see whether we can really see large asymmetries in forward direction, where the asymmetry is maybe not 0.04, but from what was published, it's maybe rather 0.4. So this is like much more favorable. We need to test that first. Yeah, as I said, this is like this is what we need: non-destructive, absolute polarization, fast measurement, bunch profile, blah blah blah. And the other thing is about polarized light ion beams, so helium-3 and blue dots. And yeah, that's the final slide. So the EIC will really be the first dedicated polarized electron-ion collider. It's the unique machine. I really don't think that it could have been done anywhere else, because the difficult component of this is not the electron part. Difficult, technologically involved, really hard component is the hard one. So I think it's not a miracle that the EIC ended up in the place where it will now be realized. Yeah, polarization is an integral part of the collider to meet the demands of the physics goals. If you take out polarization, it will just be another random EP collider. So this is really the crucial thing. We need to get this going. Thank you very much.
Hey, we have time for questions, so.
Can you elaborate what intrinsic resonance is? Because I didn't really understand it, and it seems like a very important effect.
I'm incompetent. Let me just. Here, yeah. So these imperfection resonances basically occur at integer gamma g. Yeah.
The intrinsic.
So the bottom, these imperfection resonances. The intrinsic resonances are those that depend on the vertical Betatron tune. The vertical Betatron tune is the number of Betatron oscillations per turn. So basically you have the beam on its own moving through the midplane, vertically through the plane. And this is another periodicity which you have to take into account in your depolarization. Therefore, the periodicity is here, and this is, or I think this is, yeah, and this is like the vertical tune which you have to avoid to make sure that there's no depolarization. That kind of explain it.
Why is it such a strong effect compared to the other resonances? Like, you had
I think the resonance strength is not too different. I mean, the resonance strength.
Yeah, up, that's. Two more slides.
No, here you see it. So
Oh, okay, never
the
mind.
intrinsic ones are kind of go to 0.4 maximum maybe, and these are weaker. Sure, they are weaker, but they are nevertheless there. So the primary problem is actually first to attack these intrinsic ones, and then the fine tuning is usually going to these imperfections.
Yeah. And again, if not, we can chat over coffee, but
Yes.
let's thank Frank again, so. Let's take half an hour. We'll start at 10 of, and our finale will be presentations from you folks. So we'll get to see what you're working on, and then that'll finish just in time for the 5 o'clock barbecue, which comes before the 6 o'clock rain, so it'll work out perfectly. So 10 of, thank you. Right.
My slides.
Sorry?
How do I upload my
Oh,
slides?
Well,
I'm not even.
Oh. Do that, and I'll add you to that, sorry. Sorry, I got the, sir, mixed up.
They also asked me to share my.
Separate the spin states. Because your beam coming out of the nose, it has a certain divergence. Your spin separation. We work very narrow forms called. Therefore, the stronger your field, better the
I work now.
Yeah, okay. Yeah, she already had a vote for the weekend, so.
Where?
She's at 136. Yeah, it's kind of where Sakura is this way, she's way down.
particularly.
Right, great.
I just emailed the cfns.school email.
I'll make sure you got it.
I just.
Can you do it to almost? You did it which? It has. That's okay. I got it.
You got it.
Right. Email.
EMP.
This is what we're
So you need to do is you need to make it.
It's like.
I still can read it.
Since then, the source intensity.
The RSD transformation.
That's my exam. But if we could make another step, somebody may have.
Why did they make
Go higher to 5 Tesla. Some.
It's one thing.
That would really make a difference.
Are you sure that's why you're okay? Like modern radiation. Where the T's.
It's understandable.
일단 신채널하고 리빙 트위스 리뷰는 따로 있구나.
I mean, I have to
I thought it's, I mean,
say
you know,
it's science.
Yeah.
I thought a little about it.
And click that.
아,
이거 위에 아, 오늘까지니까. 아, 오늘 왔네.
So that's gonna end it. Yeah.
저 채널.
Yeah, yeah. Yeah, as I said, this needs to be addressed. It's okay. It's not. It's not.
Then that's divide. Nineteen.
my conference presentation is just like whole slide.
Telling the people if you don't. No, they are.
Felt like I've written up something.
Thank you.
Why no?
We don't talk about it. It's not even an option when you want to.
Yeah, so it's just-
It's not an option. We need to start now.
Yeah.
Think about it.
That's
If
why
we
I'm.
paid us like
Yes.
it says for G gamma.
I will.
3 times.
이상하지 않아. 형이 자꾸 서프레스는
X. It should be plus this partial. Not the vector solution. It's possible to make organization.
17년도 두 번째.
I can see. Yeah, I think gamma G equal 3 times an integer, that's probably not really a distinction.
CD means that.
Or a 3 GDP or gammas up or down, G gamma is up or down, like G gamma is at 250 is something like 260. Or 266, something like this. So whether you run it 269 or at 263 or whatever, this is not an exponential. But this is something we should be. This is something we should be.
Just come.
I tell Elke all the time to convert that hydrogen to deuterium.
방금 용어
I just show it. This is there. It's the same thing. You don't need to think twice about it.
아,
But one should do it. And one should build a deuterium source, a deuterium source for injection, and one should really work on these things.
원래
This is the way.
옛날 저는
아,
볼륨별로 나오잖아요.
맞아요.
그거 들어가는 데가
아,
진짜 이간의 시간이.
그거는 좀 많이
아, 진짜.
그 약간 스킬가 100만 원 들고 진짜 한번 서밋 예전에 제가 계속
아,
Yeah, okay. It's also, that's not the full formula, actually. There's also new X involved. In general.
그림 보려고.
There's also some, it could also be a horizontal discussion.
그거는
Make a spin with models.
I just want to test it.
no, you give a name, something that we.
So I think it's in general, it's MQX plus NQY. Gamma AP
이거는
plus MQX plus NQY, something like that.
Yes.
I knew that's.
There's absolutely no.
I think they just care about.
A만
네. 가볼 수가 없어요. 왜냐면 산타도 일본이면 들어가야 넥스트 타이어 트위스트지. 근데 저 캐치는 근론이 없잖아. 다 컵. 근론이 없는 거야. 넥스트. 애들은 그냥 그래.
Sure, Stephanie, have to pull up the
Right.
Like these speed balls.
Yes. Daniel's around asking. I think there's an office and it's connected to Chavez. Yeah. It's an office. That's. Le Rathmann. Busy schedule. Guys survive.
Yeah. Right. I really enjoyed that. I think it's the first school only in the city. I haven't ever. Great.
Yes, he's gonna have a lot of data.
Yeah, the IC would be the best. Best accelerator for this.
It's gonna be fun.
Yeah, before this school, I didn't understand why we can use LHG, ECD. And my LHG will be enough with all of.
It's high energy, but it's doubling.
Yeah.
And question is a. Nice of it.
Yeah, that's. Be the best option. It's the polarization.
Yeah, no, yeah, it was, yeah, we had, you probably had two talks.
Yeah.
Jill, what are you doing?
I'm just taking a look at the real data right now. And so you can see the luminosity here. Yeah. Particularly. So when last week on Friday, we had a discussion with Abay. You should watch the plot more, but access it on real time.
This is real time?
Well, this is last 4 hours, last 4 hours.
Yeah.
8 hours.
That's
Last
Well,
two,
it's-
last one.
160.
Okay, let me
hours.
think. What is the seven rounds? Well. I think it's the last week, the last 7 days.
Mhm.
So what is the rank? Yes. Maybe I have to check it first. What's indicated? Well, okay, I'll do my. I got that. Yeah. Last.
Nothing on the show, but. I didn't tell you they would be, last day. If the last day I knew that.
Oh. Or otherwise you could have. Husband,
Oh, yeah.
time, cooking for.
Like, I make fun of her.
Everything. I also need to know when like there was a day. Yeah, which I spent like around 30. I want have like 8 hours. I don't know. Just giving it a try. Like I was like around 20. Then of course it is working. So I thought, okay, it's possible to spend more than 40. Yeah, they thought that's the beginning. Then that's then it's not that big. But probably they just did that because the like birthdays for the okay. Present.
Yes.
Yeah.
Does it more than 5 minutes? or-
No.
Okay,
Because,
if I go more.
whatever it's not technically well, at least even on like 7.
So I will also join. My flight is at midnight, midnight. Or no, I'll just.
Yeah. Nana, what's it?
Yeah, I took that like 2 hours ago, and I.
Yeah, it needs almost an hour to start.
Yeah. I just feel a little bit here. I know what to say.
Sore throat.
Some throat,
But
a little bit. Comparing with yesterday, now I'm better.
I'll try.
But you need to rest.
Probably, yeah, probably on Sunday. Sunday I will be so sick.
I already have to check.
There's that possibility. Yes.
Yeah, but for the air conditioner inside the plane.
Oh, yeah.
Same bus, right? Same bus.
For sure.
Doesn't matter.
And these are all.
Beto,
I have trying.
Beto, estás.
Please don't try.
Ya viste, ahí están todas las fotos.
From Jamaica,
Los recordados.
Wilson, right?
Cercan los de Creda ahí.
I think that, and then
Eh,
we didn't come, didn't, take the streamers.
Suerte que no ha llovido.
So, there was like 3 bus.
Trying to tener en el resto y ir al bench.
Yeah.
Para una
England was, yeah.
I decided to have this último juego. These are all about.
Ya, lo comes.
Yes, but when you wanna have refund. No, I also.
Oye, la verdad es que yo me acuerdo que decís profe de que memoria cuando me checar. La verdad es
Okay, so he's coming.
So maybe that helps a bit. But I
que
can't
shows
really-
sí a las.
can't really explain it.
La verdad es una hora antes. Va a estar como a las 3. Va a estar como a las 3 en el área.
Porque más tarde me da susto.
¿A qué parte vamos a ir de Nueva York? ¿Lo bien?
Because I wanted the boarding ticket.
No, vamos a dejar el pasaje cerca de Gran Central,
No problem.
porque desde Gran Central hasta mi casa empiezas a cada en plan, es como que pasan todas las branches.
Ah, pues puedes tomar cualquiera.
Entonces puedes ir a cualquiera.
Ah, eso está súper cool.
Sí, a cada 500 hay 3. Así que no.
Sí, no hay problema. Hey, I'm answer.
Going to give
Yeah, no.
I'm sorry, because I'm the third. Is there?
Do you want to be the first one?
Yeah, can I?
Yeah, of course. Let's do it. No problem. Bueno, la verdad es que me hubiera gustado haber pasado. Siempre me gusta como salir luego de eso. Que me pongo muy nervioso. Solo lo hago por eso, porque me pongo muy nervioso. Algún día se me tiene que quitar de tanto pasar. And I call.
Muy ready. How are you?
I will be the second.
Are you the second?
Yeah, I just changed the slot with another guy. You wanna be better, better.
Oh, okay.
Yeah.
Maybe 6:30.
Yeah.
Because we have the luggage and take more time to get to the station.
That's true. That's
6:30. And then we will lobby and we can lunch at 35.
okay. If you know, if you're not coming at 6:35, you just
We just leave.
okay. I will wait. If it's needed. Because you are Japanese. And you wanna go today to the French? After, yeah, after the, I think.
Okay.
Into,
And take a shower.
yeah, but probably the. Barbecue. Could be like a 6. For me, barbecue is another thing.
It's
It's another thing. It's not like grilling.
barbecue.
It's like a kind of sauce.
Ah, the barbecue sauce.
Yeah.
This is the sauce that is used
But they never
for barbecue meat. It's the
But
sauce.
we never use it. They never. It's not a barbecue.
Now for me, barbecue.
Yeah.
If you put the sauce, it's barbecue sauce.
Makes sense. See you in Italy.
Yeah, we can try. Not that short.
At the end, Axel and me, we should do the PhD. And I hope you don't fall. Probably we go to Europe or here.
But you already speak.
No, I'm the masters.
You are the master?
Yeah,
I
I just
thought-
remember 5 years, 7 years. A lot of
Okay.
time just. Yeah.
And when are you going to live?
Yeah, so Bob is over there already?
Yeah.
Bob's here. We'll be heading over shortly.
Okay, all right, sounds good, thanks.
Next year, I will start to look many
And
places.
when
I
you
don't
are
know.
graduating?
Next year, January.
Okay.
Yeah.
Because in Italy, education are.
August.
April, June.
But I was checking, for example, in Padua, and then it was not open the application.
From April. Sorry, from April to June.
Okay,
depends on-
well, now it's open.
But you are graduating.
I should apply the next year.
Yeah, next year.
Okay, I will apply the
And
next.
it will start for. April.
Four.
October.
Ah, yeah. Good.
I don't know how it works.
I don't
The
know.
application process for. Bench.
But then it's the university. Yeah, in Italy is because it's the government who gives scholarships.
You should, yeah. And that's for some Italian professor.
I have that, so that knows me in Padua, Analupat. He works in electronic things.
Electro.
Yeah, I can change, doesn't matter. Just another. At the end, it's the same, take some data, make some feeds, that's.
Nice.
It's nice, it's one of the oldest universities in the world.
Senior being. And there are a lot of thermal centers.
I'm scared about the admission process. Because, for example, in Padua, you should pass an interview. Bologna, I think you should pass not only an